The ground inside metal-clad cables must be bonded to the box. The outer sheath of metal-clad cable is not suitable for equipment grounding because it is not a continuous conductor. The ground wire inside the cable is the only reliable path for grounding equipment. When two metal-clad cables are spliced inside a box, the ground wires must be bonded to the box to ensure a continuous path for grounding current. To understand why bonding is crucial, consider the fundamental principles of electrical grounding. The primary purpose of grounding is to provide a low-impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. This rapid clearing of ground faults minimizes the risk of electrical shock and equipment damage. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding to ensure electrical safety. Article 250 of the NEC is dedicated to grounding and bonding. Specifically, Section 250.4 describes the general requirements for grounding electrical systems. Section 250.8 addresses the connection of grounding and bonding equipment. The NEC mandates that all non-current carrying metal parts of electrical equipment be grounded. This includes enclosures, raceways, and other metallic components that could become energized due to a fault. The grounding conductor provides a path for fault current to flow back to the source, causing the overcurrent protective device to trip. In the context of metal-clad cable installations, the NEC requires that the equipment grounding conductor within the cable be properly connected to the metal enclosure or box. This connection ensures that the enclosure is at the same electrical potential as the grounding system, preventing voltage differences that could pose a shock hazard. The outer sheath of metal-clad cable is not recognized as a reliable equipment grounding conductor for several reasons. Firstly, the sheath may not provide a continuous, low-impedance path for fault current. The sheath is typically constructed from a spiral wound metal strip, which may have gaps or discontinuities that increase its impedance. Secondly, the sheath may be subject to corrosion or mechanical damage, which can further compromise its conductivity. Thirdly, the sheath may not be adequately sized to carry the full fault current that could occur in a ground fault condition. Therefore, relying solely on the metal-clad cable sheath for equipment grounding is not a safe or code-compliant practice. The equipment grounding conductor, or EGC, within the metal-clad cable is specifically designed and sized to provide a low-impedance path for fault current. The EGC is typically a solid or stranded copper wire that is insulated or bare. The EGC is connected to the metal enclosure or box using approved connectors or methods. When splicing two metal-clad cables inside a box, it is essential to ensure that the EGC from both cables are properly bonded together and to the box. This bonding creates a continuous grounding path that extends from the equipment being served to the source of power. Several methods can be used to bond the EGC to the box. One common method is to use a grounding clip or screw. The grounding clip is attached to the box, and the EGC are inserted into the clip and secured. The grounding screw is used to connect the EGC to a threaded hole in the box. Another method is to use a grounding bushing. The grounding bushing is installed on the end of the metal-clad cable, and the EGC is connected to the bushing. The bushing is then connected to the box using a bonding jumper. Regardless of the method used, it is important to ensure that the connection is mechanically sound and electrically conductive. The connection should be tight and free from corrosion. The connection should also be made in accordance with the manufacturer's instructions and the requirements of the NEC. In addition to bonding the EGC to the box, it is also important to ensure that the box itself is properly grounded. The box should be connected to the building's grounding electrode system using a grounding electrode conductor. The grounding electrode system typically consists of a ground rod, a metal water pipe, or a concrete encased electrode. The grounding electrode conductor provides a path for fault current to flow from the box to the earth. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The grounding electrode conductor should be installed in a manner that protects it from physical damage. The conductor should be run in a raceway or conduit where it is exposed to physical damage. In summary, when splicing metal-clad cables inside a box, it is essential to bond the EGC from both cables together into the box. This bonding ensures a continuous grounding path that extends from the equipment being served to the source of power. The box itself should also be properly grounded to the building's grounding electrode system. Following these grounding and bonding requirements will help to ensure electrical safety and prevent electrical shock hazards. Here are some additional points to consider regarding grounding and bonding of metal-clad cable installations. Firstly, it is important to use the correct type of connectors and fittings for metal-clad cable. The connectors and fittings should be listed for use with metal-clad cable and should be installed in accordance with the manufacturer's instructions. Using the wrong type of connectors or fittings can compromise the integrity of the grounding path. Secondly, it is important to avoid over-tightening the connectors and fittings. Over-tightening can damage the metal-clad cable or the box, which can also compromise the grounding path. Thirdly, it is important to inspect the metal-clad cable for any signs of damage before installing it. Damaged metal-clad cable should not be used, as it may not provide a reliable grounding path. Fourthly, it is important to follow the requirements of the NEC when installing metal-clad cable. The NEC provides detailed requirements for the installation of metal-clad cable, including requirements for grounding and bonding. Fifthly, it is important to consult with a qualified electrician if you have any questions about grounding and bonding metal-clad cable. A qualified electrician can help you to ensure that your metal-clad cable installation is safe and code compliant. Let's elaborate on specific NEC sections relevant to this topic. NEC Section 330 covers metal-clad cable. This section outlines the permitted uses, installation requirements, and ampacity of metal-clad cable. It's crucial to understand the limitations and restrictions on using metal-clad cable in various environments. NEC Section 330.3 specifies the permitted uses of metal-clad cable. It's essential to ensure that the cable is being used in a location and application that is allowed by the code. For example, certain types of metal-clad cable are not permitted for use in wet locations or hazardous locations. NEC Section 330.30 covers securing and supporting metal-clad cable. The cable must be properly secured and supported to prevent damage and ensure that it is not subjected to excessive strain. The supports must be spaced in accordance with the NEC requirements. NEC Section 330.40 covers the bending radius of metal-clad cable. The cable must be bent in a manner that does not damage the conductors or the sheath. The bending radius must be at least 5 times the diameter of the cable. NEC Section 330.108 addresses equipment grounding. This section reinforces the requirement for the equipment grounding conductor within the metal-clad cable to be properly connected to the metal enclosure or box. It also prohibits using the metal sheath as the sole equipment grounding conductor. Now let's discuss the importance of using listed and labeled equipment. The NEC requires that all electrical equipment be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories or Intertek. Listing and labeling indicate that the equipment has been tested and found to be safe for its intended use. When selecting metal-clad cable, connectors, and fittings, it's essential to choose products that are listed and labeled. This ensures that the equipment meets the applicable safety standards and will perform as intended. The listing mark on the equipment will indicate the testing laboratory that certified the product. The listing information will also provide details on the equipment's ratings and limitations. Using listed and labeled equipment is crucial for maintaining electrical safety and code compliance. It provides assurance that the equipment has been properly tested and meets the required safety standards. In addition to the NEC, other standards and regulations may apply to metal-clad cable installations. These may include local building codes, state electrical codes, and industry standards. It's important to be aware of all applicable requirements and to ensure that the installation complies with all relevant standards. Local building codes may have specific requirements for electrical installations, such as requirements for the type of wiring methods that are permitted or the location of electrical outlets. State electrical codes typically adopt the NEC as the basis for electrical safety regulations. However, state codes may also have additional requirements or amendments to the NEC. Industry standards, such as those published by the National Electrical Manufacturers Association, or NEMA, provide guidance on best practices for electrical installations. These standards may cover topics such as the selection of wiring methods, the installation of electrical equipment, and the maintenance of electrical systems. Staying informed about the latest standards and regulations is essential for ensuring that metal-clad cable installations are safe and code compliant. This requires ongoing education and training. Electricians and other electrical professionals should participate in continuing education courses to stay up to date on the latest changes to the NEC and other relevant standards. They should also attend industry conferences and seminars to learn about new products and technologies. By staying informed and up to date, electrical professionals can ensure that they are providing the safest and most reliable electrical installations possible. Understanding the concepts of impedance and fault current is also crucial. Impedance is the total opposition to current flow in an alternating current circuit. It includes resistance, inductive reactance, and capacitive reactance. Fault current is the current that flows in a circuit during a fault condition such as a short circuit or a ground fault. The magnitude of the fault current depends on the voltage of the circuit and the impedance of the fault path. A low impedance fault path will result in a high fault current, while a high impedance fault path will result in a low fault current. The equipment grounding conductor provides a low impedance path for fault current to flow back to the source. This low impedance path allows the fault current to quickly reach a level that will cause the overcurrent protective device to trip, clearing the fault and preventing electrical shock or equipment damage. If the equipment grounding conductor is not properly connected or is undersized, the impedance of the fault path will be higher. This higher impedance will limit the fault current, which may prevent the overcurrent protective device from tripping quickly. In this case, the fault current could flow through unintended paths, such as through the metal enclosure of the equipment or through a person who comes into contact with the energized equipment. This can result in electrical shock or even death. Therefore, it's essential to ensure that the equipment grounding conductor is properly sized and connected to provide a low impedance path for fault current. This will help to ensure that the overcurrent protective device will trip quickly in the event of a fault, protecting people and equipment from electrical hazards. In addition to providing a low impedance path for fault current, the equipment grounding conductor also helps to reduce the voltage potential between metal parts of electrical equipment and the earth. This is important because a voltage potential can create a shock hazard. If a person comes into contact with two metal parts that have a voltage potential between them, they could receive an electrical shock. The equipment grounding conductor helps to equalize the voltage potential between metal parts, reducing the risk of electrical shock. The equipment grounding conductor is connected to the building's grounding electrode system, which is connected to the earth. This connection to the earth helps to dissipate any voltage potential that may exist in the metal parts of the electrical equipment. By reducing the voltage potential, the equipment grounding conductor makes the electrical system safer for people to use. Let's also touch upon the importance of regular inspections and maintenance of electrical systems. Electrical systems should be inspected and maintained on a regular basis to ensure that they are operating safely and efficiently. Inspection should be performed by qualified electricians who are trained to identify potential hazards. Maintenance should include tasks such as tightening connections, cleaning equipment, and replacing worn or damaged components. Regular inspections and maintenance can help to prevent electrical fires, electrical shocks, and other electrical hazards. They can also help to extend the life of electrical equipment and improve the efficiency of electrical systems. The frequency of inspections and maintenance will depend on the type of electrical system and the environment in which it is operating. However, it is generally recommended that electrical systems be inspected at least once a year. In addition to regular inspections and maintenance, it's also important to be aware of the signs of electrical problems. These signs may include flickering lights, trip circuit breakers, hot outlets, and burning smells. If you notice any of these signs, it's important to contact a qualified electrician immediately. Ignoring electrical problems can lead to serious hazards such as electrical fires or electrical shocks. By being proactive about electrical safety, you can help to protect yourself and your family from electrical hazards. Let's delve a bit deeper into specific scenarios you might encounter when dealing with metal-clad cable. Imagine you're working in a commercial building and need to extend a circuit using metal-clad cable. You've run the new cable to a junction box and are ready to make the connections. First, ensure the power is off to the circuit you're working on. Double check with a voltage tester to confirm. Next, carefully strip the outer jacket of the metal-clad cable, being mindful not to damage the conductors inside. After stripping the jacket, you'll see the insulated conductors and the bare equipment grounding conductor. Now, this is where the bonding comes in. If the junction box is metal, you must bond the equipment grounding conductor to the box. You can do this using a grounding screw, a grounding clip, or a grounding bushing depending on the type of box and the available hardware. The key is to make a secure and reliable connection. Remember, the goal is to create a low impedance path for fault current to flow back to the source. If the junction box is non-metallic, you still need to connect the equipment grounding conductors together. Use an approved connector such as a wire nut to join the equipment grounding conductors from the two metal-clad cables. The non-metallic box itself doesn't need to be grounded, as it's not conductive. However, the equipment grounding conductors must still be connected to ensure a continuous grounding path. Another scenario you might encounter is adding a new receptacle to an existing circuit using metal-clad cable. In this case, you'll need to extend the circuit from an existing receptacle box to the new receptacle box. Again, start by ensuring the power is off and testing the circuit to confirm. Run the metal-clad cable between the two boxes, securing it properly along the way. In each box, you'll need to connect the conductors to the appropriate terminals on the receptacles. The equipment grounding conductor should be connected to the grounding terminal on each receptacle and bonded to the metal box, if applicable. When working with metal-clad cable in damp or wet locations, it's especially important to use the correct type of cable and fittings. Use metal-clad cable that is specifically listed for use in wet locations. These cables have a moisture-resistant jacket and are designed to withstand the corrosive effects of moisture. Also, use waterproof connectors and fittings to ensure that moisture doesn't enter the boxes or cables. In these environments, corrosion can quickly compromise the grounding path, so it's crucial to take extra precautions. Finally, always remember to follow the manufacturer's instructions for installing metal-clad cable, connectors, and fittings. The manufacturer's instructions will provide detailed guidance on the proper installation techniques and will help you to avoid common mistakes. Ignoring the manufacturer's instructions can lead to unsafe installations and code violations. So, take the time to read and understand the instructions before starting any electrical work. By following these tips and guidelines, you can ensure that your metal-clad cable installations are safe, code-compliant, and reliable. Always prioritize safety and consult with a qualified electrician if you have any questions or concerns.